welcome Dr. R. Subbaiah sir for joining us for this seminar today. And I also welcome our guest speakers, Surendra Singh Kachwala sir. Dr. Surendra Singh Kachwala sir is a professor of Mechanical Engineering Department from School of Technology, PDPU, Gandhinagar. I also welcome the other guest speakers, Dr. A.G. Mahod from Dr. Balasaheb Sawant, Konkan Krishi Vidhyapith, Dapoli, and Dr. Sachin Kumar, Deputy Director of Sardar Swaran Singh National Institute of Renewable Energy from Kapurthala. I also welcome the Professor and Principal Investigator of NAHAP CAST Program, Dr. R.S. Punde sir, for joining us. Thank you very much, sir. Looking at the potential of renewable energy, and the renewable energies technologies are being used in variety of applications in farm and in farm vehicles. Looking at its potential, the development of new renewable energy technologies and its research, development, demonstration, and deployment is very much important. Looking at this need of hour, this particular seminar has been conceptualized to educate or to reach the scholars or the eminent faculty members or the upcoming research students to take up the challenging research areas to go ahead. So now at this juncture, I request our organizing secretary, Dr. Dharmesh Vyas, to present his welcome address at this occasion. So please.
Good morning to all. Respected Dr. R.V. Vyas sir, Honorable Vice Chancellor, Anand Agriculture University, Anand, Dr. R.C. Agrawal sir, Deputy Director General Education, National Director NAHAP, ICR New Delhi, Dr. R. Subbaiah sir, today's Chief Guest and Principal and Dean, College of Agriculture Engineering and Technology, Budra, Dr. Prabhat Kumar, National Coordinator, NAHAP, CAST, ICR New Delhi, Deans and Directors of the University Anand Agriculture University Anand, Dr. R.S. Pundir sir, Professor and Principal Investigator of NAHAP and CAST, Anand Agriculture University Anand, faculty members of the university, core staff of online seminar, our most valued participants and my dear friends. A very good morning and cordial welcome. On behalf of one day online seminar and Anand Agriculture University, I welcome you all to inaugural function on cost-effective and innovative green initiatives for futuristic agriculture. This seminar is sponsored by World Bank and ICR-funded NAHAP CAST project. Energy is one of the major parameters for establishing growth and progress of the country. Rather, the standard of living depends directly upon the per capita energy consumption. India is confronted with tough challenge of supplying accessible and affordable energy for enhancing opportunity for gainful employment, not only for the agriculture sector, but also for the non-farm rural economy. The national grid may never reach some communities in off-grid villages for economic and geographical reason, so that these villages are often without a reliable supply of energy for lighting homes, powering agriculture and its associated business. Most farm machines are driven by fossil fuel, which contribute to greenhouse gas emissions and in turn accelerate the climate change. Such environmental damage can be mitigated by promotion of renewable energy such as solar, wind, biomass, tidal, geothermal, small-scale hydro biofuels, and wave-generated power. These renewable sources have a huge potential for agriculture industry. Decentralized green energy, that means renewable energy sources based on sound technical solution, solid business model, and enabling policy needs to be deployed in agriculture sector. The development of green energy in agriculture will require research, development, demonstration, deployment, and commercialization of new technologies. Each of these activities must function as part of field flowing from the research bench to a commercial application with feedback loops among the various steps. The concept of sustainable agriculture lies on a delicate balance of maximizing crop productivity and maintaining economic stability while minimizing the utilization of finite natural resources, and detrimental environmental impacts. This online seminar will explore the participants, the effectiveness of green energy initiatives, technological innovation, guidelines to identify the proper design and large-scale deployment of innovative and locally appropriate technologies. We recognize that there is a still long way to go, but the goals we have set for ourselves are achievable and will have enormous benefit. Here ends the CRIPS introduction of the entire seminar. Thank you very much. Jai Hind, Jai Jai Garvi Gujarat.
Thank you very much, sir. It was just seen Dr. A.G. Mahod sir just joined. I welcome Dr. A.G. Mahod sir for joining this webinar. Now I request Dr. R.S. Pundi sir, the professor and PI of this project and NAHA project, to present his introductory remarks for the session.
Thank you, Engineer Sarvan Kumar and my colleague, Dr. D.K. Vyas, for a very nice introduction about this whole webinar. My role is limited here, but it's very, very important because once again, I welcome my Honorable Vice Chancellor, Dr. R. Vyas, who shall be joining little later. Right now, he's busy with some other activities, as I told you, and all other dignitaries, our chief guest and keynote speaker today, a very renowned person, academician, and we have no words much because we know little. And whenever we need, we are he's kind enough to accept our invitation, deliver the lectures or guide us, Dr. Subbaiah Sahab. Sir, few days back, you also delivered 2 lectures at a very small request, and you are always here, sir. Thank you very much, sir, to join us, and we welcome you to this one-day webinar, though this is your broad area, most important area, but we are here to learn many things from you and other speakers in this today's webinar. Basically, all the organizers, and I welcome my Honorable Vice Principal, Dr. Vaishi Jhala, Dr. Prabhat Kumar, National Coordinator, and all the conveners once again. The important point about this project is how this is related to this one. The basic thing is that this our projects on agriculture market intelligence is one of the thematic area which under NHP CAST component has been, I think, has been there, and our university has received this 1.5 years ago under NHP CAST. And this is on agriculture market intelligence. But all the World Bank projects, they need to address the environmental sustainability activities. And we also have in this project, one of the activities as ESP, Environmental Sustainability Plan or Environmental Sustainability Activities. And we also have one coordinator for that, Dr. Shakti Ranjan Panigere is the organizer. And that's why this environmental sustainability, sustainable agriculture, which is for that, I think green energy is very, very important as an integral part of the environmental sustainability is the most important for agriculture in general, and specifically for any project which is World Bank funded. And this our project on agriculture market intelligence is jointly funded by ICR and World Bank, sir. So that's why this is very, very important. But as far as activities, our activities under this market intelligence projects are concerned, so we have 2 major activities. One is centric to the research on price forecast, demand and supply for crops and allied activities. And it also includes global intelligence, that is trade activities, export, imports, quality aspects, marketing activities, including ENAMs, as well as our farmer producers organizations. Our most of the activities in this project are survey based as well as based on time series data. But this project is a very prestigious project funded by ICR and World Bank. So I think this environmental sustainability issue has to be addressed in all the projects. And that's why this project, in view of its significance and being a World Bank funded project, is important for all of us. We are here, sir, to listen all the speakers, the renowned speakers. These renowned speakers are there already briefed by Dr. D.K. Vyas Sahab and our keynote speaker and our chief guest, Dr. Subbaiah Sahab, about these things. And I'm sure, sir, we shall be learning something, noting down something for further improvements in our activities in this project, how we can improve our activities in compliance with the not only objectives, but sustainability activities of this project, which is an integral part for any World Bank project or maybe any prestigious project. These are few things, sir, which I had to say at my end. Once again, I welcome all, and over to you, Dr. Vyas, please. Thank you.
Thank you very much, sir, for your crisp information about this project. Now, I welcome our today's chief guest, Dr. R. Subbaiah sir, for his keynote address. Subbaiah sir will present the keynote address on the theme cost-effective and innovative and green energy initiatives for agriculture, futuristic agriculture, and followed by the expert lecture on wind energy technologies in agriculture. Now, sir, please take over the session and please go ahead with the keynote address. Thank you.
1 minute. Good morning, everybody. Is it audible? Hello?
Yes, sir, it's audible.
Yes. And whether the screen is visible?
Yes, sir.
Okay, thank you. So today the college is organizing a webinar on green energy initiatives in futuristic agriculture, particularly in collaboration with NHP CAST, which is headed by Dr. R.S. Kundir, our Honorable Vice Chancellor, who has provided me an opportunity to share my views, particularly on this webinar. I am highly thankful to him. And I am thankful to even ICR for providing this project to Anand Agriculture University. So, eminent speakers, Dr. Surendra Singh, Dr. Mahod, and Dr. Sachin Kumar, and the coordinators from the college, Dr. Dharmesh Vyas, and Dr. Sawant Kumar, and the coordinator from IABM, Dr. Yogesh Bailat. So I welcome you all for this webinar. So my concern topic is one is on the briefing on green energy initiatives, and later on I'll be projecting on the water energy for wind pumping, how it is going to be utilized. So particularly for the green initiatives, if you are knowing that the irrigation is the main sector which is consuming 21% of the total energy consumption that is produced in the state, 18 to 21% roughly. And the irrigation is mainly by, you can say, canals or groundwater. But if you see in the past 3 or 4 decades, you will see that a tremendous increase in the groundwater irrigated area is reflected. And mostly in the groundwater irrigated areas, if you see it, the irrigation systems that they are going to adopt is the surface irrigation systems, which is a very low efficient system, which is nearly, we can say, 30 to 40%. And if you go even for the modernization, it will give only up to the 50% of it. But whereas if you go for precise irrigation systems, mainly sprinkler, drip or micro sprinklers, everything, they save energy as well as they save water too, more than the surface irrigation system. And if you see the groundwater situation, we have 19.79 billion cubic meters of water available, out of which 80% is allocated towards irrigation, 10% towards domestic, and 10% towards the industries. So roughly 12.3 billion cubic meters of water is being utilized, and due of which of the over-exploitation of the water, if you see it, on an average, the per capita availability of the water in India is 15.45 cubic meters. But whereas if you see in Gujarat, it's 40% less than the national average, and roughly to 945 cubic meters per person only available. Now, the electricity. There are 2 sorts of power are being used in the agriculture. One is the electric pumps and another is the diesel operated pumps. So, and if you see for the past 2 decades, there is a drastic increase in the electric power pumps and over than the diesel power pumps. The reason being is the deepening of the water table. Now, if you see it, roughly 15.6 million electricity pumps are being operated, 8 million diesel pumps are being operated, and 0.3 million other sources are being used. And these nearly, if you see it, the electrification of the pumps is being reflected over here. And the 21 million agriculture pumps are connected to the grid power. And roughly 18.5% to 20% of the energy is consumed. 5 lakh pumps are being added annually. And the consumption is rose to 54% from 2015. And if you see local irrigation systems, highly inefficient, unreliable, and they are causing water wastage and they consume higher energy per unit delivery. And if you see the diesel consumption, it is roughly 200 million liters per year is being used, causing $2 billion on the exchequer. Now, the growth of electricity is, particularly in agriculture, it is 25-fold. It's tremendously, demand is increased, which you can reflect it from here. Now, if you see it, in 2006, the pending applications, every day the demand is going for the electricity pumps. In 2016-17, particularly in Gujarat, if you see 1.61 lakh applications from 33 districts are seeking for agricultural pump sets. Out of this, 1.32 lakhs are in pending. And the electricity tariffs, if you see, even the government is not recovering 10 to 12% of the cost of the supply, because the cost of electricity, which is being charged at 6 rupees for the urban areas, but whereas for agriculture, they are costing only 60 paisa per unit of it. Now, if you see the most pending applications, particularly the South Saurashtra agriculture area, that means South Saurashtra agriculture zone, as well as North Gujarat. Pending applications in Rajkot, if you see 12,062, followed by Banaskantha, Amreli, and the maximum number of rejected applications are in Banaskantha because of the deepening of the water situation, and the water table is not in a favor to extract much more water from that. And state government is giving a nearly 4,000 crores of subsidy to the power sector from the agriculture. That means they are paying it. And towards diesel operated pumps, the government is spending 1,100 crores subsidy, particularly for the diesel powered pumps. Regarding the three-phase supply, if you see the assured Gujarat supply, which is launched in the Jyotigram, that means in 2003, that's why you are getting three-phase electricity of 8 hours. Otherwise, where Jyotigram is not available, we are not getting 8 hours, even less than 6 hours, it is reflected. And the availability of three-phase power, particularly in different states across the country, is being reflected over here. Now, if you see it, the efficiency of the pumps is 40%, and the transmission losses are 25%. Cost of the electricity is 60 paisa per unit. So, causing the water table to be deepened very high. If you see it, so that's why the overexploitation is causing too much deepening of the water table, particularly in North Gujarat as well as Kathiawad region. And if you see it, because of this overexploitation region, even Central Groundwater Board has categorized Gujarat as 25 blocks. Out of these, 23 are overexploited in the state, and worst affected is particularly North Gujarat, where depletion is more than 100%. That means the replenishment, it is more than the replenishment of that it's gathering. And against the national average of extraction of 62%, Gujarat is using 72% of the extraction percentage. And out of this, 80% is used for irrigation. And the exploitation range from 30% from South Gujarat to 150% in the North Gujarat. And this is causing too much of scarce, particularly in the groundwater blocks, and you are going to face an acute shortage by 2025. So the electricity groundwater nexus needs to be analyzed, and a rethinking is needed in this region. If you see it, even on the energy sector, totally 150 kilo cubic meters of groundwater is being extracted with electric pump sets. 80 cubic meters of water is being extracted from diesel pumps, and the energy needed for 1,000 cubic meters to 1 meter height nearly needs 2.73 kilowatts of hours of energy when friction losses are minimum and the efficiency is peak. And the electric irrigation pumps efficiency, if you take 40%, transmission losses 25%, and if you see it, 1,000 cubic meters based on this, roughly 9.1 kilowatt hours of energy is being needed. That means that's the estimate of the government that is giving. So if you see it, for 150 cubic meters of water through electricity, even if 20 meter head is required, if you take it, we are roughly consuming 27.3 billion cubic meters of energy. If you take 40 meter head, it will be 55 billion kilowatt hours of energy is being needed. But in 2008, the Delhi Institute of Energy, that they have RAW, that has estimated 87 billion kilowatt hours of energy, particularly for groundwater extraction. But if you see whether it's 40 meters or 20 meters, the value is too low, which is not reflected. That means there is a discrepancy is there. That means either the water table must be deep or the transmission losses must be very higher. So government is not reflecting it. But if you see it, that's costing, if you see it, particularly the groundwater table, it is more than 60 meters deep. That's why this figure is coming out, and even the losses are also greater than 30% that's going to be there. So if you see on diesel consumption, 1 liter of diesel is giving 10 kilowatt hours of energy, and 80 cubic meters will cause you 4 to 4.5 billion liters of diesel is being consumed. And the carbon emission, particularly from the electricity, it is 0.4062 kg per carbon per kilowatt hours of energy. And a diesel, it is 0.0732 kg of carbon per liters of it. And electricity is emitting 5.5 times more carbon than the diesel. And this is that groundwater is emitting roughly 11.09 million metric tons of from the electric pumps and 3.29 million metric tons from the diesel pumps, which is causing, that means roughly you are accruing 4% of the total carbon emissions of the country. And if you see even pumping and conveyance losses, they are causing 50 to 70% in the total emissions of the sector. And if the second estimate is every meter decline of pumping water level will increase greenhouse gas emissions by 4.37 to 6% of the gas. That means carbon emitted in the atmosphere. And 1% increase in the diesel pumps reduce greenhouse gas emissions by 0.3%. Why we are saying the diesel pumps, they cannot go beyond certain level of the water table. That's why we are insisting where shallow water table conditions are existing, diesel pumps are being preferred. If you see it particularly eastern India, where Bihar, UP, where diesel pumps are more prevalent than the western zone. Even diesel consumption, particularly in agriculture, is releasing 33.6 million tons of carbon equivalents in the atmosphere. Now, if you see the energy usage and energy demand, we have 121 crore of populations, out of which 83.3 crores lives in rural area and 37.7 crores in urban areas. And total installed capacity of the country is, you can see, 370 gigawatts of energy is being produced in April 2030, out of which thermal power is constituting 62.8 and hydropower is causing 12.4. That means really 77% of total energy is catered from thermal as well as hydropower. And the 21 nuclear power plants are established in up to 2020, and which are producing 6780 million watts of energy. And per capita electricity consumption in India is 872.8287 kilowatt hours during 2018-19, and peak power deficit is reflected in 19 is 0.5%. Now, let us see the Gujarat energy status in 2016 and 2018. Power demand is 18,221 megawatts. Energy requirement is 400 million units in 2018. Agriculture is consuming 111 million units if it is in poor rainfall conditions, or if it's good rainfall conditions are there, it's using 60 to 70 million units in normal conditions. And government is purchasing 1500 to 2000 megawatts of energy from other states. And 1 lakh agriculture connections are given or approved in the past 6 years. So if you see theoretical energy requirement is 0.34, but actual energy consumption is 0.98 kilowatt hours of energy per cubic meters of water, particularly in the Gujarat sector. And energy efficiency can be improved, one on the power source and another on the appliances side. So that is roughly on the appliances side, and both that you see 10 to 15% of energy efficiency can be increased by replacing the existing undersized pumps with appropriate size and a new grid and low friction pipes, replacing high friction footwalls with low friction and low head footwalls, and rectifications in the energy can save the energy consumption by 440 kilowatt hours per year. Now, if you see it, existing pumps, how much is the energy consumption in kilowatt hours per year, and what is the rectified pumps, and standard new pumps and efficient new pumps. The electricity consumption over the year is reflected here. That's why we should go for efficient new pumps where low energy consumption is there. And in addition to that, if you provide non-renewable energy, it is going to save much more, and it's going to add another dimension to it. Now, on the agriculture pump sides, if you see it, smart pumps, that means agriculture pumps should be replaced with the smart pumps, which is having processing SIM card as well as smart meter systems. And these smart metering systems can save 20 to 30% of the energy from the pumping systems, and they can monitor the consumption on the real basis. And Energy Efficiency Services Limited distribute Bureau of Energy Efficiency Standard pumps. 2 lakh star pump rated pumps are supposed to be given in the Gujarat, and they need 54,000 crores for this program by the government. 30% of the energy savings by 2019 they have kept a target. This translate annual savings of 20,000 crores on agriculture subsidies, or saving 50 billion units of energy per year because of these smart energy pumps. Now, if you see the rising demand, total demand is 183.8 gigawatts of energy, and expected peak demand in 2021-22 by 295. And because of the high standard of living, that 2035 and 36, we need 690 gigawatts of energy, particularly in India. Now, that means the rising demand is there. This is on the demand side. We need additional power of 450 gigawatts of energy by 2034. 7% growth in energy supply is required if India grows at 8% of the growth rate. And electricity will be the key input in the GDP growth of the agriculture. Now, on the non-renewable energy side, we have small hydro projects, wind power, biopower. And out of this biopower, we have biomass and urban and industrial waste power and solar power. But out of these two, we can say solar and wind are major sectors where much focus is being done. Now, added gains with the renewable energy is low maintenance and repair, and you have low capital cost is lowest, particularly in the world, and you can get a pollution-free fuel source, offsets carbon footprint, no water required, socio-economic growth enabler. That means you are providing employment opportunities, particularly in the rural areas, key mitigation tool to reverse climatic change. Now, regarding the potential, particularly in the renewable energy sector, you have solar energy 750. That means existing potential 750 gigawatts of energy is available, wind 1 or 2 gigawatts of energy, and bioenergy 25, small hydro 20, tidal power is 8,000 megawatts of energy is provided. That means 15,000 megawatts of wind solar hybrid system capacity is expected to be added by 2025. Now, the target of the renewable energy is 2022, that means 175 gigawatts, and 2030, 500 gigawatts of energy is supposed to be given from the renewable energy sector. Now, the rooftop system we are already adopting, and that will reduce 70 tons of carbon annually, and 78,000 kilowatt hours of energy can be saved. And India, particularly in the solar energy sector, they are going to replace 26 million groundwater pumps with the solar pumps in the first phase. They are going to even replace, where access is not available, 2 lakh pumps are connected with the pipeline systems, which needs $1.6 billion in the next 5 years. And particularly deployment of 20,000 solar pumps are given in selected rural with access to pipe water. And this replacement of 5 million diesel pumps with the solar can save 18.7 gigawatts of installed capacity and 23.4 billion megawatts of consumed grid electricity produced from 10 billion liters, resulting in carbon emission saving reduction by 26 million tons per year. Now, particularly the wind power, that is, country is ranking 4th in the installed capacity, and India is going to attain 227 gigawatts of energy or renewable energy by 2022 as the target of 175 gigawatts of energy in the Paris Agreement. They wanted to achieve 500 gigawatts in 2030, and solar installation is increased by 360% by 2021. That is now, as a percentage of renewable energy is comprising roughly 49%, they wanted to contribute towards the power generation, and it is increased from 12.92 in 2013-14 to 23.51 in March 2020. And we are going to replace the coal plants with renewable energy sources, which save you 54,000 crores annually, and 5,000 compressed biogas plants will be set up across India by 2023. That's what is the generation. Now, installed renewable energy capacity growth rate is 17.33% from 16 to, if you see, 21. That is the case. Now, this is the solar pumping, which we are saying, coupled with irrigation systems. The Surya Shakti Kisan Yojana, which is going to be implemented, which is launched in the doubling farmers' income of it, where 12 hours assured power supply during daytime is supplied to the irrigation, and 12,400 farmers from 13 districts of Gujarat is going to be covered, and the total project cost is coming to 870 crores particularly. And if you see it, solar is really outperforming in India. Even wind power is also, it is across reaching 114 gigawatts by 2022. In October 2019, India started solar power plant in Rajasthan with a capacity of 2,225 megawatts of energy. And in June, Adani Green Energy got 8 gigawatts of solar energy project worth 45,000 crores. And the Prime Minister has already inaugurated 750 million watts of solar power project in Rewa MP. 47 solar parks with 25 gigawatts of capacity are going to be approved in India till March 2020. Then cost of producing solar power is 14% less than cost of electricity generated from the coal. And if you see, even on the sprayers also, we are using, and the cost is coming only with the battery backup, 25,000 rupees is coming, and 30-liter tank can cover an area of 25 into 25 square meters with an application rate of 84 liters per hour. And even dusters, which are being used with a field capacity of 0.075 hectares per hour, costing 9,000 rupees. And even solar dryers, they can save energy, particularly 290 to 300 kilowatt hours of energy per square meter area, and with an annual benefits of 6,000 rupees. And you can get your income of investment within payback period. Internal rate of returns is 2 years, particularly. The drying time is half of the solar sun drying, and it can reduce 1,127 kg of carbon that's being created into the atmosphere per year. And your solar dried vegetables, they have much more affinity in the international market. Some solar dryers and tunnel dryers, these are. And the important is solar power tractors, which are coming. Particularly, the cost of the solar power tractor, 2,35,000 per unit, with 1.5 kilowatt hours of energy with 20 horsepower engine. And in Rajkot, nearly, they are putting 8 acres land is already acquired, and they are going to produce by 2019-20. But Saribhai Patel is there. He is going to generate this solar power tractors, particularly in the market. Then electric fencing, solar electric fencing, which is costing 45,000 to 50,000 per acre, and which is giving electricity in pulses of 10 million amperes for 0.9 to 1.2 seconds, which is sufficient enough. And even cheaper versions are also available at 20,000 to 25,000 per acre with locally made available materials. And you can get solar milking machines at 70,000 cost, which are mobile machines. And even Karnataka government is giving subsidy to 50%. And even Gujarat government is thinking on the same lines to extend the subsidy, particularly these milking machines with the solar power operated machines. And you can couple these machines, even already mechanical systems are there. You can couple these mechanical machines with the solar power. Now, even wind energy installed up to in India is 37,744 megawatts of energy is produced up to March 2020, accounts for 23.5% of the installed power capacity and 43.4% of the renewable energy capacity. And then even out of RE 175 gigawatts of energy that is targeted, 60 gigawatts are going to be from the wind energy. That's what by 2022. Even if you see it, wind energy potential at 50-meter hub height is 49 gigawatts, at 80-meter height 102 gigawatts, 100-meter height 302 gigawatts, and at 120 meters 695 gigawatts of energy is there. And if you see the cost of the wind power, it is coming 3 rupees per kilowatt hours, which is lesser than, you can say, even in coal or even. These are some of the wind potentials at 100-meter height, which is accumulating to 302 gigawatts, particularly in India. And the wind power installation, the cumulative installations are go on increasing, and the cost is go on decreasing, particularly in wind sector. The contributions, 48 point, that means you can say 10%, and about 2 million jobs are particularly going to be created in the next coming decade, particularly for the wind energy. So this is what we have to save water or save energy, then and then only the sustainability of agriculture will be there. So this is what I wanted to point out, particularly for the, you can say, the lecture. And the second lecture, which we are going to share, is my wind energy topic, which is going to be taken today, that one. Now, this wind energy, we are celebrating 30th June 2018 as Global Wind Day. Now, the topic is wind, an answer for energy transition in agriculture.
Yeah.
This is an ancient, the old windmills that are being existing in different countries is shown here.
Sir,
Yeah,
sorry, sir, your screen is not visible.
Achha, screen is not visible. 1 minute, 1 minute.
Yeah, that's fine, sir.
Is it visible now?
Yes, sir.
Okay. So some of the wind farms that are existing, particularly in the wind that is in Tamil Nadu, Karnataka, Rajasthan, and Gujarat is shown over here for your reference. Now, Government of India has launched Fifth Wind Resource Assessment Program in 1985, and they have installed 50 meters towers, and they are monitoring wind speed at 10 meters, 20 meters, and 30, 40, up to 50 meters continuously from 1985. Totally 794 wind monitoring stations are established up to 2014. Out of these 237 stations, they have the wind potential of 200 megawatts per square meter. And the Tamil Nadu Muppandale wind farm that is in Tamil Nadu is producing 1500 megawatts of energy. That is an offshore wind power plant. And Jaisalmer, 1064 megawatts of powers of energy with the largest onshore. And Brahmanvale wind farm in Maharashtra, Damanjodi in Odisha, and Tupalhalli in Karnataka. They are some of the famous wind farms that are existing in India. Now, some of the wind farms that are existing in, we have particularly in Gujarat, where we have 1600 kilometer area, particularly on the onshore. So a lot of potential is existing. That's why Gujarat government has already initiated, and they have installed 12 wind farms, particularly in the Gujarat, particularly in the onshore. Target and reforms which are going to be taken: 22 gigawatts are under implementation, 5 million jobs to be created in next 20 years. Even Gujarat government is taking the Land Reforms Act and evacuation policy, particularly for the government. And you can say, carbon credit, that is the emission is that they wanted to reduce by 15% from renewable sector by 2020 of it. Now, if you see onshore and offshore, onshore life is same, but cheaper foundations in the onshore, cheaper integration with the electricity grid network, but particularly they generate noise. That is the one of the drawback, particularly on the onshore. The offshore, stronger than the onshore, power is very high, production power capacity is high, and it is much more, that means 50% more energy than the onshore. Consistent wind speed is there. Strong wind produces 3.5 megawatts of energy per hour, but the foundations and they are expensive to build and difficult to maintain, particularly in the torrential rain conditions. And if you see the blade diameters, they are changing from 15 to 120 meters with the height ranging from, you can see 15 meters to 140 meters of height. And for various power generation, whether it's 500 kilowatts to 2500 kilowatts of energy, what should be the rotor diameter that is needed? What is the swept area at 40 meter height, 54 meters? That is shown over here. Now, if you see the wind power density classification, we have 7 classes at 10 meter height, at 15 meter height, and you can say in 100 meter height, and 10, 50, 80, 100, and 120. So these are some of the heights which we are giving, particularly for the wind power classes. And the wind power classes, you can say, and if you say large scale wind plants, they should have rating more than 4. Now, what should be the minimum wind speed that is required for optimum area? That is 3.6 meters. Economically viable speed is 5 meters per second. Acceptable is 10 meters per second. Optimum speed is 15 cubic meters per second. But because the output power, if you see, it is directly proportional to the cube of the speed of the wind. And particularly you need to limit the output power, particularly in the high wind conditions, to prevent the mechanical damage. This is the wind speed density, wind power potential, particularly in India, where the potential, if you see, Karnataka and Gujarat, Rajasthan, and the western coast. That is the potential area where you can see it. But if you see on the eastern side, you are not exploring much, particularly in the renewable energy sector. This is the installable wind potential at 50-meter height, particularly. This is at 80 meter, 100 meter, and 120 meter heights above ground level, particularly the potential of wind. Now, if you see it, the wind energy, you have the main, these are some of the horizontal axis and vertical axis wind turbines are there. Then the main is, you have the components, the transformer, the tower, the gearbox, and the rotor blades, nacelle, hub, yaw mechanisms. These are some of the important components which are to be taken care. If you see the nacelle, where the design is shown here, where the nacelle is counterbalancing your rotor, your hub as well as the wings, which is containing main shaft, gearbox, brakes, and generator systems. Yaw mechanism is considered over here. Particularly, this is the yaw mechanism for keeping the rotor towards the wind direction. These are the main components: foundations, towers, blades, hub, nacelle, generator, gearbox, which I have shown you, controllers. Now, particularly the foundations, if you see, it is based on the turbine size, depends on the weather conditions, type of soil, and terrain topography. And in normal conditions, if you see it, 50 feet by 50 feet by 30 feet deep block is of foundation is being provided. The tower is kept is in that, and bolts, long bolts to the bottom of the foot is given. And there, if you see it, this is the foundation which is being given for the windmills. And these are the bolts which are being long bolts to the bottom of the foundation. They will be there. They will be tightening this. And these bolts are covered with a plastic cover to prevent from corrosion. Now, towers, if you see, you have different types of levers, lattice towers, tubular towers, guide towers, and hybrid tower concepts are also existing. But we are going mostly for the tubular towers. These are for the, if you see it, the lattice towers are used for overhead electrical transmission lines. They are metallic bars bolted together and welded together. These tubular towers, you can say, in shorter segments, and they are bolted together, and they are easy for transportation and manufacturing it. And tower diameter ranges from 10 to 14 feet, and they are always tapered in sections, and with a bigger diameter at the bottom and lower diameter at the top of it. These are the hub, where the blades are fitted, attached to the gearboxes with a low speed shaft, and that again connected to the high speed shaft through the gearbox. And the hub and blades rotate together when turbine works. And the nacelle, it is consisting, this is totally the part of nacelle, from this part completely, which is taking care of it. We are low speed shaft, gearbox, high speed shaft, as well as brake assembly completely is considered in the nacelle. It adjusts the turbine orientation to the wind direction, and it counterweights the balance for the hub and blades of it. The gearbox, if you see it, here the rotation of this one is low shaft is there, that is 20 to 50, and the second shaft after the gearbox, if you see it, it is 1000 to 3000 RPM. So gearbox is increasing the speed ratio from 1:75. That's what. This is your 20 to 30. This is 1000. This gearbox is considering 1:75 ratio. This is the yaw mechanism to orient at the bottom of it. This is orienting the hub towards the wind direction for getting maximum power. And classification, if you see it, the micro turbines, small scale turbines, and large scale turbines, where the output power is ranging from 10 watts to greater than 1000 kilowatts even. So if you want to, for low purpose and small scale operations, micro is used. For household purposes and small battery checkup, small scale is, and large repair wind generation is needed, and wind power generation is there, where you can use large scale wind powers, wind turbines. Where if you see large scale, the tower height is ranging from 70 to 100 meters, 120 meters, and small scale, the tower height ranges from 1.5 meter to 20 meters, that is. But if you see based on criteria, one is either for electricity generation or for mechanical energy for pumping of the irrigation water, based on the generator and the classification. Number of rotor blades, single, twin, 3, 4 blades, like that. Based on orientation of the wind relative to wind direction, upwind and downwind turbines, and rotational speed, low, medium, and high speed turbines. And based on the rotation of axis, horizontal and vertical. Now, these horizontal axis is, you can say, these are your horizontal axis, and here is your vertical axis. This is your downward direction. This is your upward direction. Horizontal axis where minimum drag losses are there, higher efficiency and power coefficients is there, and the complex design procedure is there and expensive, and it emits noise due to rotational speed. You need some cylindrical furling system, particularly to protect the turbines from wind, strong winds, particularly in the onshore turbines, and it needs yaw mechanism to orient your turbine towards the wind, and it can be classified as horizontal and vertical. Now, single blade systems and multi-blade systems are there, and with electricity, if you want turbine for electricity generation, you need to have more than 3 blades. These are type of blades, and horizontal axis, wind axis, and different sorts of vertical axis turbines are there. These are various types of vertical axes. These are some of the Darius rotor, Savonius rotors, vertical axis systems, and even H rotor systems are there, which are used. These are Musgrave turbine rotor systems. Now, the vertical axis turbines, you need to, they can be, the generator and gearbox can be placed on the ground. No need for a tower in this. And AIA mechanism is not needed in this. But wind speed at ground level is very low. That's why the power output will be low, particularly for the vertical axis wind systems. And that's why even rotor efficiency as well as output power is also low. And it needs some self-starting mechanism to initiate whenever it is stuck up. And second thing, guy wires are needed to support the structures. And the important thing in the design, that is winds shear. That means our monitoring, generally we are doing at 10 meter speed. But if you want at the height of 120 meters, you have to extrapolate this wind at that speed. So that's called wind shear. That means the distance of the wind speed variation with respect to the height is, you can see it here in it, which is changing in an exponential manner. But wind shear, it is velocity increase with the height, but this depend on the roughness of the terrain. And if you have dense vegetation, then the variation is low. And level and smooth terrains, they generally don't affect much effect on the wind speed. But this terrain surface roughness is generally represented by roughness class and roughness height. Now, if you see height versus velocity, the exponential variation on one side, another school of thought, you can say exponential variation they have given with a different slope. Now, the roughness length and height is, that means the height at which the effect is 0, that's what is the roughness length. Now, the roughness class, roughness length, and the shear coefficients, particularly for wind shear, you can calculate based on the description. Now, if you don't want this table, based on roughness class and roughness length, if you have defined, various formulas are existing that I will show you to later on. Now, how to find out a particular wind velocity? If you have some reference velocity height is there, if you wanted to find out the reference velocity at that, because ultimately the power is proportional to 1/3 cubic power of the speed. That's why you have to find out that power at 100 meter or 120 meter. And this alpha is called as Hellman's exponent. So this is at what height you are needing. This is the reference height at which you are measuring your wind speed. That is, this is the height at which you are measuring and the height at which you are needing it. But the alpha value generally, we consider if you don't have any value, you can consume, that means we can roughly assume 0.1 or 1/7 if it is a stable atmosphere where you can change in stable atmospheric and wind consistent conditions are there. But it depends on generally terrain and atmospheric conditions change this one. But I has given in 2007 for various areas the alpha value Hellman's exponent. Now, if you want approximations, the rough value is 1/7, which you are saying. But this you can extrapolate when wind speed conditions are needed only measuring at one height, 1. It underestimate when the stable laminar flow conditions are existing and overestimate when mixing and convection are there in the wind speed. And the approximation 2, if you wanted to extrapolate 10 meters to 15 meters height only, any height, suppose one reference height is you have one value, another value, if the H2/H1 is satisfying this condition, then and then only your approximation of fixed value can be taken. And if you don't want any values, if you want lot of formulas are existing, you have correlation based on the surface roughness, based on velocity height and reference height, which is developed in 78, 75. Nearly 10 formulas are given by Spera in 1994, which are developed. I have not given, but the important two formulas which are latest, I have given it to you. Now, one is power law, that is this called is power law profile, the wind shear, and another is logarithmic profile variation, where you are at any reference height, this is your base height or reference height, velocity at which you wanted to measure it, and the reference velocity if you know it, and accordingly if you know how the surface roughness length, based on that, here z0 is the surface roughness length. At 100-meter height you want your reference height at which the speed is 9 meters per second. Based on that, the logarithmic law can be used to find out the wind speed velocity at any height. This is what is the Hellman's exponent. Another value, this is another formula particularly used for the wind shears. This is another formula for wind shear which is used. They are all either logarithmic or power law. These are the reference length. Now,
Dr. Sarwan? Dr. Sarwan, can you hear me? Dr. Sarwan, you may ask, sir, there is some problem, technical problem. Hello? Hello?
Sir.
Dr. Dharmendra, yeah, please ask them. There was some technical.
Yes, sir. I think some internet connectivity
Yeah,
problem.
please ask them.
Sir.
You can write one line in this chat book also.
Okay. सर एक बार बात कर लीजिए
Hello, Sravan Kumar. Is it working? Hello.
Some technical problem. He's working on that.
Sir, I think there's a power failure, and it's because of that internet connectivity has gone, and I've connected through other source.
So
Shall we?
you can if time may take, so you can continue with the second session. That is, if possible. Mohod is ready.
To first one. Yes.
Just we ask.
Mohod sir is here, no sir?
Okay. Okay.
हाँ. So आप इसमें आ जाइए.
Okay.
Sir, in a moment, I'll start the Subbaiah's message.
Contact Subbaiah Sahab and you write one line in chat box.
Yes.
So that the audience can understand. So there is some technical problem. Just
I presented that, sir. Chat box में लिख दिया.
yes.
Sir, वो नहीं हो तो आप मोड से स्टार्ट करवा दीजिए.
Hello.
Hello.
Subbaiah સાહેબ join થઈ ગયા છે.
Ha. Okay.
Okay. Hello. Subbaiah સાહેબ.
Hello.
Okay.
Is it visible?
Visible. We can hear you, sir.
Okay, no problem. Okay. So now very important aspect, particularly in see it, what is the probability of the wind to get a particular optimum level that needs to be analyzed. That is a very important issue, particularly in the wind speed distributions. In all, we have Rayleigh's distribution as well as Weibull distributions. Both distributions, they give very good estimates when the wind conditions are steady and better. But at low speed wind conditions, both are giving poor estimates. And you can say Rayleigh's distribution is just a particular case of wind speed distribution when shape factor is less than, when shape factor is 2. Now, if you see the probability density function, particularly for Weibull distribution, this is the probability density function, and this is your cumulative density function, where K and C are the shape and scale, that means location parameter, K and C are. Now, K is the shape factor, C is the scale factor, and if you wanted to say location parameter is also there, 3 variable distribution, you can take that also. But for K is equal to 1, Weibull becomes exponential. If you put K is equal to 2, Weibull becomes Rayleigh's distribution. And if it's K is greater than 3, then Weibull approaches Gaussian distribution. For various values of K, the probability values, the probability density function is shown here, and the cumulative density function is predicted on the right-hand side of it. Now, for various speeds, you can see how the probability Weibull distribution curve changes. You can show over here. Now, these are some of the properties: mean, median, mode, variation of the, particularly the Weibull distribution. 2-parameter Weibull distribution is there. And now you have K and C, which are shape and scale parameters. How to distribute this one? You have particularly 2 ways of approach. One is graphical methods and another is your analytical methods. Now, even in graphical methods, you have 2 approaches. One is Weibull probability plotting position, and another is where you just plot that one in a Weibull probability paper using double lock, and accordingly the slope as well as the intercept can be taken as the scale and shape parameters of the distribution. And another is, you can say, particularly for the plotting position, generally we have certain formulas are there. You can take mean rank, median rank, and symmetrical cumulative distribution function, particularly for the effects value in the graphical methods. And you have a lot of other formulas are there. Even you can see Chicago has given lot of formulas in 1981 for plotting the Weibull distribution for the 2-parameter values. Now, the second thing is hazard plotting position. The hazard function particularly is defined as a probability function, density function to 1 minus the cumulative density function of it. So accordingly, the probability function is defined, and accordingly the hazard function is defined, and the plotting can be done based on the each failure. This is the procedure which is given, and we can easily find out even using the hazard plotting technique. One is graphical plotting and another is hazard plotting. And if you want this one, the hazard plots can be given even in SPSS and other softwares they are giving, particularly the plotting positions, particularly for this. Now, for analytical methods, you have standard deviation method, method of movements, least square method, maximum likelihood method, various, even you can see principle of maximum entropy, method of mixed movements, as well as L movements. All are existing. I am not going in detail of all this one. I'll just show you what are the prevalent methods that particularly the wind generation people they are using. This is the standard deviation formula, standard deviation method that is being used for K and C, particularly in the probability density function. This is your standard deviation. This is your mean of the observations, where the gamma function is used. This is your K, your scale parameter, shape parameter, and this is your shape parameter, and this is gamma density function. Based on this, you can find out the K value, and this K value can be substituted. All Weibull parameter functions, if you see it, the estimation procedures are completely implicit. They are not explicit functions are existing. But if you want a C value based on your average mean speed as well as K value in the probability density function, you can find out. And the rough approximation for K can be taken as rho v by Vm. That means Cv to the power minus 1.090. And the procedures for Cv and your V all are given on the side of this. Now, the second is standard deviation method, where C is given and the accurately another approximation is given for C is shown here. This is the maximum likelihood estimator. That is, here is also implicit equation, and you need numerical analysis, particularly Newton-Raphson method for estimating this maximum likelihood estimators. Now, the Weibull parameters for maximum likelihood, when some of the people they are giving in intervals. So based on the frequency intervals, if it is given the data, then you can accordingly use this method of maximum likelihood estimator for frequency values. This is the least square method. Least square method is also nothing but plotting on an ordinary graph on the log and estimating based on the here you need to have a y bar, x bar, and this beta, and these are nothing but beta and n are nothing but K and C, scale and shape parameters. That's all. Now, if you want simple approximation methods, this is energy pattern method, pattern factor method that is developed by the wind energy engineers. Particularly, they have developed energy pattern factor for here. This is now, if you see it, why they are using this cubic power average. Now, if you calculate average wind speed and you calculate average power, now for a particular wind speed, you have taken one particular power, V1, V2, another speed S2 is given, but the power is given P2, and now you make it average V1, V2 up to Vn values. The average which you are getting and the average of the power, they never match. That's why it is called root mean square speed. They have mentioning it. Now, what they want is you make the cubic power of it, and the cubic root of is to be taken for average value. If you take that one, and then accordingly, the average power as well as average wind speed, they will be matching. So that's why the energy pattern factor method is given as the cubic power average of the cubic power and average of the normal cubic of the normal average. That is taken. The ratio of these two is taken as energy factor, and based on that, the K and value is determined, and based on that, the C value can be determined. Now, these are some of the approximations, but instead of using approximation methods, you can use L movements. L movements is defined particularly in 1985, particularly by IBM people. And you can use that one. That is a very simple approach. You can use probability of weighted movements even 2 for estimating the parameters. And it is not necessary that Weibull 2-parameter distribution is only to be used. You can use any sort of distribution provided the chi-square test, Ks test, as well as Anderson-Darling test. If they are satisfying, you can use any sort of distribution, not necessary. But wind generation engineers, they are saying Weibull 2 parameters as well as Rayleigh distribution is giving good performance. This is what the statistical validation after fitting the distributions. This is some of the methods which we are showing. Based on that, if a particular distribution is fitted, then you can say what is the value. If it is speed is from 4 to 25, what will be the power I am going to get? You can find it out through the Weibull probability distribution. And if you say that if what is the probability of getting more than 16 meters per second, based on that I should make my design, then also you can make it here. So between 4 to 25, what is the probability? Greater than 24 hours meters per, that means meters per second, or greater than 35 meters per second, what will be the probability? You can estimate accordingly. And Raleigh's distribution is just a modified way where K is putting it equal to 2. And if you put those value 2 here, based on that, you can determine your probability density function, cumulative density function. And based on that, you can find out what will be the power output based on Raleigh's distribution for between two particular values, and above certain value, how much is the value, you can find it out. Now, based on this, for various revisions, for various months, at various different height, what will be the average value and wind with speeds that are given. And if you see at various probability levels, what will be the value of the speed at a 50-meter height, particularly in different village, that means places. Now, if you know the probability density function parameters K and C for Weibull or Rayleigh, you can determine what will be the power. That means rho A V cube into Cp. That is the actual power that they are being used. If you don't want that equation to be used, but if you wanted to find out based on the scale and shape parameters, you can find it out even based on the Weibull as well as Rayleigh distribution. Now, if you see it, this is what I am saying, root mean cube speed, which is defined in the your energy pattern factor methods, which is V average, how it is to be, the root mean cube speed, how it is to be taken. That's what. Because if you want average speed and average determined and average power that is determined, if you wanted to match these two, then and then only they can be used. Now, another value, air density, generally we take 1.29 value, but nobody gives you any value. But the standard value which you can take is 1.225 at 15 degrees temperature. That is the pressure, and at a pressure of 1.225 kg per cubic meter. But that is the reference value, you can take it. Based on that, you can find out density at any value with the temperature variations even 2. Here you need, what is that means? Elevation above the your ground level, and rho 0 is 1.225, you have to keep it. And second thing, how rotor diameter is to be adjusted. Rotor diameter means the available power from the wind, and if this is only for pumping, I am concentrating particularly for the pumping, but for wind generation is there, then accordingly, electricity generation, accordingly you have to take care of the efficiency of the rotor, efficiency of the pump, that means generator, your electricity, everything, all those values, efficiencies are to be taken, and accordingly the rotor value is to be decided. Particularly, this is the hydraulic power, this is the wind power, matching this one, and if you say 5-meter rotor diameter, if it is taken, accordingly you can type it out. You equate these two, put rho W is 1000 and 1.207 value. Generally for Indian conditions, we can take 1.29. If you put those values, you can find out rotor diameter, and particularly for wind generation in your horizontal axis, you can take pi by 4 into d square. So d is your rotor diameter accordingly. The important factor second is CVF, that is called capacity factor, which is to be taken. Capacity factor means what is the total. Suppose your windmill is operating for, that means maintenance hours are 200. In a year, you have 8,660 hours are there. So 200 hours of maintenance is if it is removed, and percentage of hours you are getting 97.71%. Now capacity factor, you are taking 2 million watt of per hour windmill is taken. Total power to be generated is in a year 17,520 megawatts. But actual power produced is 4,000. That means 4,000 divided by your actual power will give you 22.83%. That is the way how to calculate your capacity factor. If you don't have any capacity factor, if you don't have any output, you can take these rough values from the European Association, which he has given for various coastal and onshore and offshore areas. The very important thing is, second thing is tip speed, which decides you number of blades as well as your capacity factor. Your CP can be calculated, your CF can be calculated, or CP can be calculated based on this. It is nothing but the wind speed at a tip to the wind speed available at the hub, or downstream to the upstream. That is, and this can be calculated by 2 pi nr by v, where n is the rotational speed, r is the radius of rotor, your angular velocity, and based on that, if you don't have any values, you can presume 1 to 4, and for fast runners, 5 to 7 6 tip speed ratios can be taken. Now, if you, how to calculate CP? This is, you have taken your CF. CP is another important parameter which BETS has defined, but recently in 2008, one equation is given based on tip speed ratio. That CP, which is called as BETS limit, it can be calculated as 1 plus lambda into 1 minus lambda square by 2. Now, if you want optimal value, you can differentiate using calculus of variations, dCB by dl lambda, and equate it to 0 and find out the value of lambda. If you find out based on that calculus of variation, the lambda value will be coming 1.3. So that optimum value, if you keep it here for CP, you can get 16 by the value, you can then roughly get 16 by 27 CP. That means the maximum power that can be extracted is 16 by 27. That's what your BETS has given. Albert BETS, who is a German physicist in 1962, that's called BETS limit. So he has given based on some theory, but really with a tip speed, it was modified and accordingly it was shown. He said that 59.3% of the actual energy cannot be converted more than that. That's why he has limited that coefficient. And if you see it, even based on this, that's what I am saying, ratio of output power to the power available, that is defined with the, if you know the tip speed, based on that tip speed, you calculate your CP. Based on that, you can calculate your total number of your blades that can be taken for a particular pumping. And theoretical maximum value is 0.59, which is given as BETS limit. But in practical design, it's always less than 0.5 for high speed 2 blade rotors, 0.2 to 0.4 for slow speed wind turbines with more blades. But if you take exactly 0.5, the power output can be 0.25 into rho into V cube per swept area. So even based on the tip speed, you can find out the value of CP for horizontal wind axis, vertical axis rotines, Savonius rotors, that is given here. Now rotor swept area, this is for vertical and this is for horizontal rotation. For both, you can find it out. Now, there is a difference between the windmill efficiency as well as the, you can say, your aapka CP. Windmill efficiency is nothing but if you take it, it is the efficiency of converting wind energy to meet energy. But if you take it mechanical efficiency also into account, then overall efficiency will come. Or roughly you can say 50% of the BETS limit can be taken as your efficiency. That means 18 to 19% or 18 to 20% is the maximum value that is available for overall efficiency of the windmill systems. If you don't have any value, then accordingly you can take 18%. Now, you can say 35, this is what we have given it to you. Now, for wind pumping, this is the case of a horizontal rotor system, vertical rotor systems. This is your vertical, this is your horizontal rotor systems, and how the pumping systems can be taken. Now, if you take it, what is the daily volume that is available? If you know the head, based on the speed, you can design how much is the, if a particular head is there, for a particular wind speed is there, you can find out what will be the daily volume that is available towards the irrigation. This is a simple way of giving particularly per particular wind yield. Now, if you say it here, pumping conditions are there, you need to have drinking water supply, livestock watering, irrigation, drainage. For how much flow rate is needed, for what much of height. If you want a drinking, it's a low flow rate with a high head. Livestock farming, you can go for low flow rates as well as medium float and medium heads. For irrigation, you have to go for a medium or high flow rate. And for drainage applications, you need to have a high flow rate with low head combinations. Now, what is the type of pumps for low and high, low Q, high head, medium Q, medium head, high Q, high head? What are the type of pumps that are to be used for with the windmill that is shown here? Now, certain windmill operators, they have given their broad specifications, output versus head, and suitability they have given for different types of windmills that is shown here. Now, how to synchronize, if you see it, how to make irrigation planning, particularly for the windmill systems, you have to do the irrigation planning based on the wind speed, find out hourly discharges that is available, then accumulate for 24 hours a day. Either you consider overall efficiency fixed value or calculate based on the Q. You can make whichever is opted to you. Calculate potential of transpiration per day, decide the irrigation frequency, and you can say then based on that volume of demand can be estimated. So here is a case of a recurrence interval is given on one side, estimated discharge for 24 hours wind speed is given. Now for giving irrigation, you can find out the area based on auxiliary storage reservoir system. Now, how to find out area? What should be the size of the auxiliary reservoir system? I'll explain you right now. This is the way how to calculate the wind power. This is half Wg rho A V cube. And if you say that the rotor G value is 9.8, 1.29 is the value of the density. And if you put, and if you have rotor diameter of 5 meter, which is used for the irrigation systems, accordingly, you can get the power as P is equal to 1.38 into 10 to the power of 5 AV cube. And accordingly, the useful water power is given. And if you put those values, you can get this. And ratio of these two is nothing but is your efficiency of the system. Or if you want efficiency to be a variable, you can find out Q. So out of this equation, either Q or your efficiency, one parameter is to be fixed. And based on that, your velocity of the wind as well as head of the water, if you know it, accordingly, the discharge can be calculated. Then if you have suppose 3 meter head, 4 meter head, 5 meter head, 6 meter head, water table is there. And accordingly, the wind speed is available here at 24-hour speed. And the total heads are known. And based on that, estimated volume can be calculated based on the above. Now, suppose if you have night hours or wind hours, day, in particularly in September, you have 72 cubic meters of water is available for if you take day's wind speed at 3 meter height, if you take night wind speed, that is going to be reduced. And if you take 24-hour wind speed average is taken, you can get more. So more the discharge availability and more the area that can be irrigated. This is a case of irrigation scheduling. Now, if you say total head is 3 meter, volume of water availability is 65 cubic meter per day, roughly, you can say here in November, where pre-sowing irrigation is there. Depth of irrigation we are taking in surface irrigation, 75 mm is the minimum value. It is not necessary we should go for 75 mm, you can go for 60 mm even too. So this 75 mm divided by, that means your total amount of water divided by amount of water per irrigation, and that will give you total area in a day. And irrigation interval multiplied by that one will give you total area that can be taken for a particular crop of it. So if you take the total 24 hours average, then your area can be enhanced. Now, if you want the same design in a probability way, here the wind speed is given, intercepted wind energy, the discharge is known, then water power head, how much is calculated, water power is coming. So overall efficiency of the system is nothing but your wind energy, water power divided by your wind energy, that will give you, that is your overall efficiency and the energy consumed. Now, based on that wind velocity, how much is the wind output is given, that is plotted over here for operating head of 10 meters. This is a frequency classification of the wind. I'm saying you that you use wind probability Weibull distribution of 2 parameters. Even for frequency intervals, you can find it out what will be the probability of those values, and accordingly you can use that one. Now you have the wind speed availability. Now I want that the reservoir capacity for storing that water, and what should be the minimum cost of it, and at what probability level. Suppose if a person comes, sir, I don't want any risk. So you can go for people, you can categorize based on the economy, risk aversive, risk neutral, and risk bearing type. So based on type of farmer, you can say the design, and accordingly the risk variation can be taken, and you can take utility function of that to decide your probability level also. That can be utilized in optimization. So here what the case was done, which was done by us, we have taken different risk levels, 50%, 70%, 90%, 100% risk level is taken, and the demand was varied. Demand was calculated. How demand was calculated, that I'll explain you. 4 demand levels were taken. 3, you can say 4 probability levels were taken. That means roughly 20 possible combinations, 5 into 4. You can 4 risk levels, 5 demand levels. That means 20 combinations were taken. And based on that, the total cost was taken, and minimum total cost was taken as a criteria for deciding the optimum size of the auxiliary storage system, particularly for irrigation in the windmill systems. Now, here I have taken a case of how a particular demand is there. Demand you can estimate using your PET as well as crop coefficient adjusted to the local conditions. Based on that, the demand can be estimated. So if demand is known, you are saying, suppose I am taking my 40 cubic meter demand is there. I will take 70% probability level, which is a probability level which can be taken by anybody else. The daily discharge that is available during different dates in the January was taken. So 40 cubic meter reservoir capacity was taken, and this is the availability. What is the deficit that was calculated? So you find out for all these cases, for different daily demands, for different risk levels. So the reservoir capacity can be plotted accordingly. So accordingly, we have plotted this one. Now, based on that, the reservoir capacity is known. You have the capital cost of construction and excavation cost is there. That means one is on the investment that you are making on the windmill. Another you are putting on the reservoir system. You have to couple both those. Then you have to bring that one to the annual cost of system. And that annual cost of system will be added with the operation and maintenance cost accordingly. So if you see it at different risk level, daily demand was taken, capacity of the reservoir was taken, cost of the construction, annual reservoir cost, capital cost of the windmill, annual cost of the windmill, annual maintenance cost, coupled with these two, the total cost is coming. So if you see, the total cost it will be optimum at certain value. After that, it starts increasing. So based on that, the value will be decided, and accordingly it can be taken care. Now, based on this is one way. Accordingly, I have given case studies, particularly for daily, if a reservoir is having for fish pond, how much amount of what 20 cubic meter per day is given. If you know the alpha Hellman's exponent, which you can assume either 0.1 or 1/7 or any of the value, based on that, your power from the wind, hydraulic power can be calculated, discharge per cubic meters per second can be taken, and based on that, what will be the effective windmill rotor area and diameter of the rotor can be estimated. Now, the second thing important is cost analysis, which is very important. Now, here, if you see it, the lifetime analysis, life cycle analysis is very important, particularly for the wind energy systems. The life cycle analysis, you need to have the cost of the capital is given, and price of the turbine, foundations cost, all these coupled, the cost of the capital, that is the total cost, the capital cost is given. Then wind installation costs are there, operational cost per year is there. This operational cost plus capital cost per year will comes to total cost. This is the on the energy side, annual energy production, and cost and energy production, the revenue you can get, how much is the profit that can be generated. Now, if you see it, the percent contribution of the cost, particularly in the windmill system, particularly for the windmill generation, this is the cost split up. Rotor assembly will cost you 25%, nacelle will cost 15%, electrical power equipment 15%. Likewise, the split up of the cost, particularly for power generation, in this land cost is not included. Okay. Then the next is for different kilowatts of turbine. If it is 3000 kilowatts, if it is 30 kilowatts, what will be the power split up, cost split up in various components of the windmill system is quoted here for different rotor diameters and for different height of the towers. Now, if you see it, particularly government subsidies, you have 45,000 to 1,50,000 rupees is there. In addition to that, foundations they will be giving 20,000, 20,000 to 20,000 for tank installation foundations. Repair and maintenance cost is given 2,000 to 3,000 rupees. Subsidy is 50% extras on the work pumping and subjected to the ceilings of 20,000 to 30,000. And for direct drive and all these things, you can say even 45,000 is giving. For non-electrified islands, it is higher. This is totally the subsidy schemes that is being given. And if it is a hybrid systems, wind solar hybrid systems are there, then what should be the cost that is giving? 2.5 lakhs to 3.5 lakhs per kilowatt hours, depending on the ratio of wind and solar components. And cost of installation civil works, 10,000 per kilowatt hours of subsidy is giving from the government. Repair and maintenance cost, 3,000 rupees per kilowatt hour per annum is given. And X cost works and R&D works, either 50% or maximum ceiling of 1.25 lakhs per kilowatt hours is being given. And for non-electrified or for where power is not available, the subsidy is enhanced. So these are the depreciation values, particularly that are being given. You can take for maintenance of cost of requirement, maintenance cost, annual cost. Now, if you see, some people say that this cost is compared when wind, geothermal, biomass, your wave power, photovoltaic, tidal and hydropowers are there. You can see the lowest will be coming hydropower. And based on that, after that, the wind power is only coming. So people should think of even solar photovoltaic system is there, photovoltaic cells are there. But if you can think of that also, wave power, that's costing 4 cents per kilowatt hours of energy. Now, if the height is increasing, your capacity factor is increasing, that means increasing, that means output power will be increased, cost will be decreased accordingly. And based on the tower height accordingly, cost per kilowatt hours will be also decreasing. This will be a inverse quadratic function which you are getting it. Even if you see the costs over a year, historically, they are reducing particularly for the renewable energy, and cost of fraction for the past 15 years, if the project life is increasing, the cost also will be decreasing of it. Accordingly, wind velocity, rated power outputs, I have given you. One important analysis I am giving here. If you want, there are two cases. I am saying I have certain, that means I have, suppose you are saying I have 3 lakhs of amount. Based on 3 lakhs, what should be my power efficiency? I want capacity factor, how much is the value? Or if you have capacity factor, what should be the optimum money I should invest? In both cases, we have given a formula to calculate if money is available, how to capacity factor is calculated, and if capacity factor value is given, then how to maximum investment that can be made, that is shown here accordingly. And based on this, you can, this is a value where money capacity factor is given, and based on that, even money, how much is to be invested, and what will be the, based on that, you can find out internal rate of returns. So the gainsays are easy land acquisition approval process that is initiated by the government. Agreements on power purchases. Right now, they are purchasing at 3.8 to 3.9 per kilowatt hour is being purchase value. Competition from the solar. Growth rate of wind power is half of the solar only. But if you see, I have shown you that the comparison, if you see it, in solar, it is 21 to 81 cents per kilowatt hour. But whereas in wind, it is 4 to 7 only. But the initial cost is very higher. That is the only. And second thing, the land requirement is a very important concern, particularly for the wind. That's why government is working out on this. Then the main users. You have, it is not necessary, we have to have all the wind energy density at all places. So we have to find out, I have told you that a minimum is you need to have 15 kilometers per hour of wind speed is needed for economically viable systems. Low energy density is one of the criteria. Require energy storage systems for environmental pollution, which is causing environmental pollution. Turbine rotors extract only 10 to 40%. And you have told you that beds limit is there. You can't go by 16 by 27 of the available power. High initial investments, irregular wind speeds, and that is one. And because of irregular wind speeds, as power is directly proportional to the cube of velocity, so you are getting an irrated output power and a linear increase with the weight and size. Huge quantities of concrete and your foundation requirement is needed, and the too strong winds can be spoiling this. So this is what is my concern. So I have explained to you the cost considerations in the auxiliary reservoir systems. without auxiliary reservoir systems, how to match area of it, how to design a wind rotor systems, hydraulic systems, what are the components of it, the government subsidies, and all the economical feasibility I tried to focus here. So thank you very much for patiently hearing me for such a long time. And I'm thankful even to our speakers, your Surinder Singh Saab, as well as Dr. Mahod from and Dr. Sachin Kumar, who have readily accepted for giving their expert opinions, particularly on the wind, solar power and wind power. Basically, I am a man of solid water engineering. I am not a man of energy, but with interest only, I am working on solar water pumping and wind energy pumping systems, and how to couple even wind energy pumping with the drip irrigation energy and low energy drip irrigation systems. Also, we are working it out. That is, we wanted to do it. Thank you very much.
Thank you very much, sir. Lastly, again, it's a very informative session. Being a man of soil water engineering and delivering such a wonderful lecture from energy with a lot of data. It's wonderful, sir, and it's very apt for our session also. Thank you very much, sir, for that keynote address. Now, before going further, before concluding this inaugural session, let me quickly go through that particular itinerary, today's itinerary, how it is going to be. I'll let you know. After this inaugural session, we'll be having a technical session 1 and before lunch. And after lunch, we'll be having technical session 2 and 3 starting from 14:30 hours. So I request all the participants to stay connected accordingly. Now I request our Dr. Lard, sir, to please propose a vote of thanks. Dr. Lard is a joint organizer and after joint organizing secretary of this particular program, and is also CC and PI of this session. And after this vote of thanks, we will have having a technical session 1. Sir Lard, sir, please go ahead.
Okay. Thank you, Sawant Kumar. At the end, I think for the inauguration, for the very good lecture given by the Subbaiah Saab, I propose my vote of thanks. I first of all thanks to our patron, Dr. Vyas Saab, Honorable Vice Chancellor of AAU, as well as the National Coordinator, Dr. R.C. Agrawal, for his continuous support, and he ignited us for organizing such an event which will be dual helpful, that in NHP we have an environmental guideline we have to follow. It will be enhance our knowledge for the next upcoming year for the upgradation in the agriculture. We also like to thankful our Dr. Y.C. Jala sir, who is the Dean IABMI, and Dr. Prabhat Kumar, our National Coordinator. They are busy with some meetings and everything, but they given our well wishes. Thank you very much, sir, for their kind words. I would like to thankful our convener, Dr. R.S. Pundir sir, PI of NHP Cast, Naheb Cast AU, for his welcome address, as well as the key things we have done in the NHP. I would also like to thank our organizing secretary, Dr. Avias, who is DK Vyas, who is put his, you can say, from last 1 month he's trying for this webinar, and right now I think we are witnesses very good speakers and everything. Thank you. I would also like to thank the Dr. Sakti Ranjan Panik. He is the environmental coordinator in the Naheb Cast. He's put his effort for all these events. Also, I would like to the Dr. Sawant Kumar. I think he has taken too much pain from last 15 days to make this event. And also, I would like to thankful to the, I think, beloved Subbaiah Saab to give a keynote address on the topic which I think sir can do it. So thankful to sir. And also I welcome and thank the Atul Mahod Saab, who is going to be delivering the first technical session. Thank you very much. Over to Sawant Kumar, to you.
Thank you very much, sir. Now I welcome Dr. Atul Mahod, sir. He's a head and a professor from Dr. Balasaheb Sawant, Konkan Krishi Vidhyapith. Sir, thank you for joining us, and we welcome you for this session, sir. I request you to please take over for the technical session 1.
I'm audible?
Yes.
Good morning, Subbaiah sir.
Arey, namaskar, bhai, Mahod.
Long time to see you healthy and in, as usual, in a light mood. I'm thankful to Mr. Vas, PI of the NAHP and ultimately the Anand Agriculture University. I will share my screen. Is it visible, sir?
Yes,
sir.
yes.
Hello.
Yes, sir, it is visible, sir.
Yeah. Good morning to all. After hearing an in-depth and a vast experience person's lecture with all type of data and all type of calculation, I remember the Dr. Subbaiah's speech, and at every forum he spoke mostly on the technical knowledge. Maybe whatever the forum, but he doesn't left any of the point where the engineer shows his modeling and simulation and all type of mathematics and everything. But looking towards the topic, what the task is assigned to with me, I'm try to give my presentation on a different look for that one. No doubt, the solar photovoltaic energy is abundantly now it is utilized. Government is very pressing hard to promote that one, and that will give you the one of the technology which can fulfill our dream in the near future. Whatever the Dr. Subbaiah says, even he goes to around 2025, 2030 or even 2034, a huge amount of energy is required for us and for in all every sector. So ultimately, when we go for the just a minute, sir. We know the basic need of civilization: food, fiber, and shelter. Right from the roti, kapda, makan. Nowadays, we require a clean and cheap energy in every sector. It may be a transport, it may be industry, it may be agriculture, or it may be a household sector. And there are only two types of energies are available. We say that either it may be a renewable or either it may be a non-renewable. Either it may be a polluted one, either it may be a non-polluted one. Types of energies are different one. Any country which is having their own resources, own feasibility, they can use the type of the energy. But ultimately, only the basic classification of the energy, what we say is either it is a renewable or either it is a non-renewable energy. Either go for the with the nature or either go for the against the nature. Now, if we look at that one, in each and every sector, we require a power. It may be a transport, it may be industry, it may be a domestic, it may be agriculture or anything. And we know that the power which is required for everyone, for every country, that must be a clean, it must be a secure, it must be a cheaper in rate, and it must be timely assured in every sector. If energy giving during the night time for the irrigation of the pumps, that doesn't mean the solution. One has to give the timely energy for each and every sector. And particularly when we say that agriculture and related to the domestic sector, it consumes more than 40% of the energy in India. Now, if we look at the power generation, the huge data is shown by the Dr. Subbaiah, but the peculiar characteristics is that more than 60% energy which is generated in India is fossil fuel drain. That may be the coal, that may be the hydro, that may be the some part in nuclear, or that may be your natural gas or the diesel, and it creates the huge potential. It caused the climate change. What we observe, a cold wave, what we observe, the heavy rainfall, cloud bustering, etc., etc. And particularly, these fossil fuel power plants are centralized power plant, which causes the transmission and distribution losses to the tune of around 35%. This is the countable. What Dr. Subbaiah is saying, uncountable transmission and distribution losses, we doesn't know that one, that figure. And there is a need of reliable action in a near future to fulfill our demand, as there is a limited time period is left for the different type of the fossil fuels. That may be the coal, natural gas, crude, Hydropower, it is around 84,000 megawatt in capacity is there. Period left is infinite one, but still there is a conflict between whether the hydropower or the water is go for the irrigation or drinking or industrial purpose or for the power generation, and then redistribution of that one. Nuclear power, with that we know that it has a infinite capacity, but still there is a security reason or there is a concern of the security in that source also. So based on this one, particularly when we focus for the energy in agriculture, it is observed that it is a vital component in a farm mechanization. And particularly in India, 85% of the small and marginal farmers are away from the proper, secure, timely assured and clean and cheap energy sources. If you look at the mechanization level in India, which is till date, it is only up to 40%. Till we achieve the 40%, and in 1970, 0.29 kilowatt per hectare is the power consumption in a Indian farms. Maybe somewhere in Punjab or in Haryana, it may be higher. In other state, it may be the lower one. Whereas in 2019-20, it reaches up to 2 kilowatt of the per hectare power, and it is estimated that in 2025 it will be reaches to 2.5 kilowatt per hectare power in a farm. And this is the predicted one. So for this purpose, we require a secure, we require the clean, we require the cheap, and most important is a timely assured energy for the particularly for the agriculture sector. Now, if we look at what the mechanization level is there. Now, if we look at the share of the mechanization in India, 90% is through the machines. A agriculture worker and draught animals not contributing more than 10%, or even a labor or the animals is not contributing more than 14% of the total share, and machines are contributing around 90% of the power. And out of that, around 50% power is shared by the tractor and the power tiller. Rest of the 16% is diesel engine and 27% is the electrical motors. And it is evident that if we look at the mechanization level, particularly in India and in Indian agriculture, most of our mechanization is focused on the tractor or the tillage and the seedbed preparation. And we hear that green color dot or green color line shows the level of mechanization achieved. And it is observed that in a tillage and seedbed preparation, even though out of total 40% mechanization level, 90% by the machine, and out of that around 70% is given by the tillage and seedbed preparation. Rest of the things which are fertilizer application, irrigation, harvesting, post-harvest requirement in this sector, or even in a plant protection level, interculture operation, there the green color dots is very less than even 50% or less than even 25%. That means there is a huge scope is available in the sector of mechanization of your fertilizer application, irrigation, harvesting machineries, post-harvest mechanization, or even in an interculture operation. And it is observed that all these operations, that is fertilizer application, irrigation, harvesting, or interculture or post-harvest operation, doesn't require a energy more than 3 kilowatt of the power. Whatever 3 kilowatt per hectare is the maximum power which is required for these of the operation. Now, my point is, we are putting the energy in agriculture. We are saying as the mechanization level goes on increasing, we require more and more energy. Or in a reverse case, if it is the energy input in a agriculture sector or in a farm, kilowatt per hectare is to be increased, then and then only it is possible to increase the mechanization. And we are focusing the mechanization mostly on the tractor. And tractor is only used for most of the operation of the tillage and seedbed preparation. And we are lagging in the mechanization of other operations of the agriculture which required low power, and there the diesel and electricity are the major contributor in that. So if we look at, can we think that one, that our agriculture is shifting or there is an end night for the diesel engine? We are, and particularly this one, why I am saying this one, Dr. Subbaiah is also shows the electrified tractor or SPV opter tractor. A large corporate manufacturers are moving towards the electrified machines. Either it may be a small tractor, either it may be a power tillers, and either it may be an engine, or either it may be electrical machines. And it is observed that in a next decade, the Indian farm will consume, or it is shifted, or it increased the electricity consumption from 16% to 27% of the total energy required in the farm. And that is the indication that Indian agriculture is shifting from diesel to the electricity in a near future. Now, if it is we are shifting to the electricity, why we are shifting to the electricity? Because it has a particular advantages of that one. The electrical engines can generate a 4.3 kilowatt per kg of the weight, and that is 3 times more than diesel engine. So in a same weight, we can generate a higher 3 times more power per kg of the weight of the machine, and it is 40 times smaller per kilowatt of the diesel engine. This is the one of the reason why we are shifting to the electricity. Second thing is the efficiency of the electrical motion is machines is around 85 to 90% as compared to 35 to 40% of the diesel engine. And agriculture required 0.5 to 3 kilowatt power for most of the operation except the land preparation or the traction work that is done by the power tiller or by the tractor. And the modular size and robust nature of the electrical machines are very suitable for small and marginal farmers and widely adopted. It is observed that in the past decade, the small and marginal farmers preferring the smaller machines, smaller tools that is operated by the electricity rather than the bigger tractor, because of the ideal period of the tractor is very high. And for that purpose, we require the constant and secure supply of the electricity in the farm if we want to increase the capacity, if we want to increase the intake of the power into the farm. Naturally, most of the data which is presented by Dr. Subbaiah has already shown that whatever the discount everywhere, that is not in the Gujarat, that is not in the Maharashtra, in all over the country, each and every distribution and distribution companies or electricity distribution companies are in very much threats of the economical threats. And if we require the electricity from the farm, we need 7 times more than the present figure. Whatever the electricity we are consuming now if we change to the electricity, we require 7% more. And our problem is around 69% is we are generating the electricity from the fossil fuel, which resulted in a huge transmission and distribution losses. On an average, there is a 11% shortfall of the electricity supply is observed on an average, and it consumes, the farms consume, or the farming sector consumes around 18% of the electricity and contributing only the 5% of the GDP of the nation. And that gives the bigger eyes of different sector on agriculture, the industrial sector or transportation sector, constantly questioning the government that why you are giving the free subsidy or the free power to the government or the agriculture sector, because they are not giving much more GDP into the nation development. And it is observed that the demands will be doubled in the next year. And if it is electricity is required, the subsidy and theft and unmetering will lay down the DISCOM into the heavy burden, and that is not the good sign for the Indian agriculture. The Niti Aayog, or we can say the Niti panel, recommended that let the farmer pay for the power. Power subsidies up till now in a 2000 around 17-18, the power subsidies processed up to 90,000 crores of the rupees that we are giving to the farmers, and the burden of this one is on the industry and high power consumers. And naturally, the tariff rates of the industry, if it is increased, transportation rates is increased, ultimately it will goes for the inflation rate, increase in the inflation rate. And for this purpose, the challenge has to prolong. One is we required uninterrupted electricity during the daytime in the farming sector. And second thing is we have to prevent the rising demand from the agriculture to bleed DISCOM further. Further, pressure on the discom we cannot give, or we cannot say the maximum pressure should be given on the discom so that it will give, it is on the version of the collapse, and for that purpose we required another option for that one. Now coming to the topic, if this is the situation, we had a very ultimate soul. We are enough fortunate that India is blessed with the sun. And the solar energy India, even it says that 10% of total energy received on India, if it is used, which is having on an average 1.3 kilowatt per square meter, even 10% of it is used, we can solve our problem forever. It is clean and pollution free. It can be decentralized in nature. It is almost available 300 in a year. There is no distribution and transmission losses is occurred if we install a solar power plant. Cost is competitive with the other sources. It is scalable. Most important, it is scalable from few watts to the megawatt. It is having a very low gestation period. If it is a coal-based power plant I want to install, there is a rehabilitation of the people. There is a threat to the climate. There is a nature damage. Instead of that one, a solar PV power plant is having a very low gestation period without rehabilitation, without harming to the nature. There is no displacement of the people, and most important is it has a huge potential for the empowerment of the rural youth or the local people. So this is the source ultimately we have to use for that one. Now we know that as a for the student it may be solar energy, it is having a major application, either it is a thermal application, either it is a electricity application. For the temperature wise, it may be the low temperature, medium temperature, high temperature. I am not going in detail of that one, that is what are the different applications of that solar thermal application. Whereas for the electricity, either it is a standalone system with a DC or AC power, or either it is a centralized power. Solar PV can be classified majorly in two sectors. One is either it is for the individual one, or either it is for the centralized one. And no doubt, whatever the appliances are available in an agriculture field that can be operated on the solar energy, solar photovoltaic energy. Only the problem is feasibility of that particular application with the investment into the solar power plant. It will generate the DC electricity, can be converted. Now, if it is good for the solar photovoltaic, there are different classification of the solar photovoltaic system is there, and solar photovoltaic sector is the most economical and fastest growing technology in the world. Only 10%, I say that only 10% of it can solve the problem forever for our country. There are different applications are there. Either it can be used directly, maybe for the solar pumping system, mobile charging, solar lantern, sprayer, winnower, cream separator, milking machine, grass cutter, hydroponic unit, solar signal lighting, warning system, CCTVs, and many more. Whenever there is electricity is required, we can provide the electricity by using the solar photovoltaic system. Either it may be a standalone system, it may be for the domestic application, it may be for agriculture, or it may be for the hospitals. Either it may be off-grid system, again classified in major portion, that is off-grid system. It may be a standalone or a hybrid system, or it may be a on-grid system, maybe the rooftop system, maybe the power plants, larger solar power plant. Already Dr. Subbaiah has given you the very much good data regarding the what the government is taking the initiative of that one. I'm not going in detail of that one. Technologies goes on increasing. A number of types of silicon cell or solar cells are currently available in the market. Many more are coming into that. Ultimate aim is to make the increase in the efficiency and reduction in the cost. Efficiency in the last 4 decades, the efficiency of the solar panel is increased from 8% to maximum up to a 42% of that one. A organic solar cell with a nanotechnology is achieved up to the 42%. Still, it is not commercialized one. The energy cost is reduced from 40 rupees per unit to lowest of it one, that is around 15% less than the coal-based power plant per unit cost, that is 3.5 rupees per unit. The solar PV is reduced up to that one. Industry is doubling in every 2 years. for the students or for the agriculture sector, or particularly for the agriculture engineering, this is one of the sector where the integration of the solar photovoltaic system for the agriculture purpose is very much needed, and because this is the industry which is doubling every year in a huge manner all over the world. Now, one of the concern is that to reduce the cost and to increase the efficiency, and there is in a upfront cost is people are working, or the research and development wing of the solar photovoltaic system in a worldwide is working on the three components. One is the semiconductor material, which may be a technology related to the chemical engineering or electronic system. Second is area related cost, that may be the reduction in the cost of the glass, installation, real estate, and the wiring. And third one is power related cost, that is the inverter. And there are two options or two strategies for the reducing the cost is that reduce the semiconductor material. Nowadays you can observe that the solar panels are reducing in the size day by day, but the efficiency goes on increasing, and reduce the area by increasing the efficiency. This is the two way we can reduce the cost of the solar photovoltaic panel. The second is two primary concentrating approaches are there, that is increasing the concentration or increasing the solar intensity by concentrating the solar radiations on a smaller area. So high concentration area and the low concentration area, that will increase the input over the panel. Cost of the panel is reduced by size as well as by increasing the concentration. So in this way, the efficiency as well as the cost of the solar photovoltaic system is, people are trying to reduce the cost further for the wide adaptability. There are different type of the systems are there. Maybe for the student, I hope students are also watching this one. Either there is a on-grid system, there is a off-grid system, and the solar power plant can be hybrid type or the standalone type, which can be used for different appliances in the agriculture sector. There are proven applications are there. Till this date, this is the duty of agriculture university also that one has to give the maximum field data, field application data of solar photovoltaic panels for the different agriculture sector. And till this date, 4 or 5 technologies which are mostly related to the agriculture, a charging of the battery or the lighting of the farmhouse may not be a pure agriculture applications. Particularly agriculture application or the farm operation based on the solar photovoltaic system need to be more and more tested and evaluated, feasibility tested in the ground, so that the wider adaptability is there. And in that one, the solar pumping system is one of the technology which is technologically proven, feasible for the farmers. Maybe there is a conflict between the system integration and the selection of the farmer, everything, but it is a proven technology that yes, it can be used for micro irrigation, it can be used for sprinkler irrigation, and that can be adopted widely by the farmers. And it is the most proven and widely adopted technology in the rural area. It is ranging from 1 HP to the 10 HP, even up to the 15 HP, and heavily subsidized and promoted by the government. This technology still, it is under promotion of the government of India. One more technology for the small and marginal farmer is the solar PV operated solar sprayer. A huge amount of energy is required, or manual energy or fuel energy is required for the plant protection appliances, and the solar photovoltaic based powered spraying system or different type of sprayer, on an average around 16 types of the sprayers are already in the commercial market, and that is proven technology. That is, yes, solar photovoltaic can be used for the agriculture application for the plant protection appliances. This is the second technology in my view. Maybe different technologies are there. The third one is the solar fencing for the protection of the wild animal. This is the biggest threat nowadays for the horticulture crops also, as well as the commercial crops grown by the farmer, which is a very high value product, and threats from the wild animal is very high. And there is till this date a fencing with the solar is one of the solution for that one. Now it is also widely adopted. It is totally operated on the solar. There is no threat to the animal, but it will protect the your farm from the wild animals. It is having a low operating cost and can be widely adopted. This is the third operation. What I think is, this is the third operation or third field operation where the solar photovoltaic can be used. One more technology is coming in the picture nowadays in a cold chain marketing, that is the solar photovoltaic based cold storage unit. This is also a direct application of a solar photovoltaic. It is a transportable unit having the capacity of 5 tons and above, and the temperature maintained is around 2 to 4 degrees centigrade, and it is a 2x7 cold storage facility for the farmers, for the vegetable growers, for the fruit growers, and there is a need for the adoption of this technology widely for the application of the solar photovoltaic energy, so that ultimately we can increase the share of the energy into the farm as well as share of the solar photovoltaic energy into the farm, so that the farmers may not be get reliable on the DISCOM or the government for the uninterrupted power supply or the secure power supply or the cheaper power supply. So all these are the 4 technologies at this moment is looking very prominent for the agriculture, that solar photovoltaic can be used. If we look at the overall photovoltaic system, it has the slide shows the solar power can make the production a few large power, instead of few large power plant, we can go it for the mini solar power producer along with the wind supplier also, or wind power also with the hybrid system. Second thing is, the market of the existing power plant is centralized one, and mostly it is a national one, whereas solar energy is having a potential that it is a centralized and ignoring the boundaries, and it creates the chain of power plant, or it creates the one can say grid of the power plant at the decentralized level. The third major component of the power is the transmission. Existing system of the transmission is based on the large power lines and the pipelines for the petroleum products as well as the electricity, whereas the solar power can have a potential that include a small scale transmission and regional supply compensation. It will reduce the transmission and distribution losses. The fourth one is the existing power plant of the particularly fossil fuel power plants is from top to the bottom. It is created somewhere else. From the top level, it goes to the bottom level. Whereas in a solar power or in a solar photovoltaic based power plant, it is from bottom to the top also, and top to the bottom also, by using the rooftop solar system, or you can get the net metering system. Here from the bottom also, you can generate the electricity and send it to the top management. And from top management, whenever you require, you can get it to the at the end user applications. And particularly for the consumer, existing system is very passive and it is only paying type of the system. Whereas when we go for the small solar power plant or the chain of type of solar power plant, it is an active system. A producer or consumer is also an active one in that one, and participating in the system. Also, it is getting the money if we sell the power to the grid also, or to the power distributors, etc., etc. Now, this is gives you the overall advantages of the solar power system over the existing power system of the our national grid. That it will in a production, it will facilitate the production at the smaller level. It will give the market. It will at the wider level. It will reduce the transmission and distribution losses. Distribution is from the both side, either from the top to bottom and bottom to top, as well as the consumer is also paying, getting the money, not only paying, but he is also getting the money if he is using the solar power plant. Now, if we look at what the emerging power technologies nowadays coming on the agriculture sector. Individually, the maintenance of the SPV pump by the individual farmer is difficult nowadays because of the theft, because of the over exploitation of the groundwater, because of the idealism of that power plant during the winter season as well as during the off period. Any solar pump which is installed having a 5 HP or 10 HP pump, if it is a solar energy is available right from morning 8 o'clock to the evening 5 o'clock, the people are exploiting the groundwater, and that also creating the threat to the future agriculture also. So for that purpose, nowadays the emerging solar PV energy technology is coming in picture, and that 3 technologies, that is, first one is the solar agri feeder. It is a micro power plant installed and managed by the DISCOM, not by the individual one, and transmit the energy to the farms only. It is purely for that micro power plant of 1 to 10 megawatt will be installed in that vicinity, and that connection is given only to the farms, not for the industry, not for the transport, or not for the domestic sector. And this is 1 to 10 megawatt capacity community power plant. It is linked to 11 kilowatt station, substation and the feeder, and 1 megawatt power plant required only 2 hectare of the land, and it is useful for supply of the heavy machinery also. It may be pump, it may be thresher, it may be your dairy, it may be your poultry. Everywhere you can supply that electricity. And it is estimated that a 1 megawatt of a power plant in that vicinity can energize your 350 pumps of 5 HP pumps at a time. And electricity power will be given for the 2 hours, 3 hours, or maximum 4 hours for the irrigation, and rest of the time that power is goes for the different other operations. And it alleviates around 26 million tons of the greenhouse gases. Now this type of system is already launched in the Maharashtra as a one of the initiative. And 4 to 5 solar agri feeder power plant systems is under construction, and in the near future that will give the result how that community solar power plant for the farmers, dedicated to the farmers, will give the better result, or may give some difficulties or that one. The second technology is this is also one of the technology which is nowadays coming into the picture, that is the transportable solar power plant. We know that a small and marginal farmer doesn't require more than 3 kilowatt power for 70% of his operation. Other than the seed bed preparation or the your tillage operation, rest of the operations are of having a capacity not more than 5 kilowatt. Either it may be a 3 HP pump, either it may be a 2 kilowatt base thresher, either it may be a thresher, either it may be a winnower, either it may be a grass cutter, either whatever the operations are there, it is within the range, or the matrix of Indian agriculture shows that it may be right from the drone application to the spraying operation, right from threshing, winnowing, or post-harvest operation, or your poultry, dairy. On an average, it required, a small and marginal farmer required up to 3 kilowatt of the power. And instead of installing a 3 kilowatt power plant in his individual farm, a transportable 3 kilowatt power pack is the nowadays it's a tool for the custom hiring for the remote areas. A one power plant, he can transport it to the application site, he can thresh his grains, come back to the its original place. There is no theft, nothing is required. Capacity carries around 2 to 3 kilowatt by using the solar photovoltaic panel. It is available in both AC and DC in a both format. Tracking mechanism for the better output, and it is modular in nature. It is a theft preventive, on-site and multi-purpose tool coming into the picture. And this is the second technology what I observing in the solar photovoltaic, that one is community solar photovoltaic based agri feeder, and second one is the transportable solar power pack, just like a tractor, like a custom hiring. And the third one is, one more technology is coming into the picture, that is the solar agri production system, or simply it is called as agro photovoltaic. That is the combination of a photoelectricity and agriculture production on the same land. There is no extra land is required for this one. 30 to 35 area land cover will produce the sufficient to manage the rest of the things in the farm. Extra power can be stored or supplied to the feeder using the net metering system for the further gain. In my view, these are the, in future or in the next decade, these three technology will create a different picture in Indian agriculture, that community power sector, community feeder or the power plant by the DISCOM for the energizing of the nearby vicinity farms. Second one is the individual one, power pack of around 3 to 4 kilowatt maximum, which can transportable in nature. And third one is the solar agro photovoltaic system, which can generate the power from the same land with the power also, which can be used for that same power can be used for the managing of the different operations in the field. This is the one of the agro photovoltaic system where you can operate the machines, you can generate the power, and you can take the crop also. Overall, the power is very crucial in the agriculture sector. Slowly we are shifting from diesel to the electricity for the future farm mechanization, and for that version we required a secure, reliable, cheap, and all-time 24/7 electricity on the farm. And for that purpose we required a ultimate source that is, fortunately it is available with us, that is the need to use the solar power. Thank you. I finish here. I hope what the need, what is the present situation, what the need, and what the agriculture engineer should think, particularly those who are working in the renewable energy sector should think in this manner, that maximum applications, field-based application of the solar photovoltaic, unless and until you are not showing that one, you are not showing the viable and commercial application of that one, there will not be a acceptance of agriculture. Particularly I am using it, maybe the hard word, agriculture engineer may not be get absorbed into this sector, which is mostly related to the agriculture. Thank you very much.
Yes, sir. Thank you very much, sir, for that wonderful presentation. As you promised at the starting of this presentation, you have added color, green color for this green technologies through your presentation, sir. And you have already highlighted the research scope, where exactly it's not actually the solar PV system, it's actually the timely energy generation what we require. It's very much important as per the demand, particularly for agriculture and the farm mechanization, where 24/7% of electrical motors are can be act as a crucial role. Also shifting from diesel to electricity and feasibility to application, the research on the feasibility to application point of view, and how to tap 10% of solar energy effectively. It's again, it's a kind of a research scope. Also integration challenges we are facing nowadays. And the key take-home points are the fossil fuels are unidirectional, whereas the renewables and particularly solar is a bidirectional. So thank you very much, sir. And the way you presented the emerging technologies also again, solar agri feeders, solar PV systems, transportable, and agrivoltaics. These are really emerging topics where the agricultural engineers can be a crucial part of these researches. So thank you very much, sir.
Thank you very much.
Now I request all the participants will meet a post-lunch session, which is starting from 2:30 today. And you might be having already got your registration link for the technical sessions 2 and 3. And see you all in the next technical sessions at 2:30 p.m. Thank you much.
Thank you.
Thank you, sir.
Thank you very much.